And now we'll look at compounds of silicon with oxygen, a large group very important chemical compounds named silicates. There are literally hundreds of thousands of them. To start with, silicon dioxide, simply silicate or silica itself, can react with hydrofluoric acid, but not with any other acid, to form SiF6 anion, making hexafluorosilicate acid, which is strong acid, contrary to usual silic acid. In this compound, silicon has relatively unusual environment of 6 fluoride ions, and that's possible because fluorine is smaller than oxygen. Nevertheless, this compound easily decomposes on heat, giving SiF4 gas when it's hot, which is tetrahedral compound. The usual coordination number of silicon is 4. Silicon tetrachloride, same tetrabromide tetraiodide, quickly react with water to make hydrated silicon dioxide. Upon heating, you can make anhydrous SiO2 of these. It can be made non-crystalline gel, and there are plenty of compounds based on silica gels as main way of purification of silica for manufacturing purposes. In SiO2, as we have seen, the coordination number of silicon is 4, is surrounded by 4 oxygen atoms. Silica also react with sodium hydroxide or with sodium carbonate to make water and different silicates. In silicate, the main building unit is this tetrahedral, like that. This compound itself is so-called silicate glue, and in fact it is not monomeric, it's polymer of SiO4 units glued together. There are different compositions depending on relative number of sodium oxide and silicon oxide H's. For silicates, the building unit will be SiO4 with minuses on each oxygen, and common way to draw it is such a notation, having dot on silicon atom and a circle on oxygens. They are seldom monomeric, so Si2076 minus will be drawn like this, and they are tetrahedral. More complex structures are having layers of tetrahedra with empty space in between that can be occupied by metal ions. It can be different types, so very simple formula like Si2O5 in fact is an infinitive two-dimensional layer of silicon oxide tetrahedra. Aluminum can replace silicon in some of these tetrahedra, making alumosilicates. And this again is an enormous class of compound known in geology. Now, to balance the charge, we need to add positive ion because aluminum is 3 plus, not 4. So large potassium or sodium or calcium ions will occupy empty space in crystal structure. They have generic name feldspar, German for field spot. And each mineral has its own name. There are literally thousands and thousands of them. Very interesting usage of aluminosilicates is making of porcelain and ceramic. The starting mineral is kaolinite from Chinese value kaolin, and it's alumosilicate with some water. Water can be removed by roasting, and then a further process remove silica. It can be some different additives. As a result, very interesting, beautiful crystals, needle-like crystals form that makes all material fantastically strong. Real hard porcelain is pure alumosilicate, and it's semi-transparent. You can see through it. Making it is still, always was and still is, a very complicated process. So for cheaper similar product, we use so-called bone china using calcium phosphate plus glass. This is not porcelain itself, but some qualities resemble it, and most commonly we use this specific for kitchenware. Glasses itself are silicates having mostly SiO2, some calcium and some sodium, with very little other admixtures. So essentially it's calcium sodium silicate. In SiO4, silicon can be replaced by bore. You remember diagonal analogy between boron and silicon. In this case, when you put around 10% of boron instead of silicon, this is by weight, by molar it will be around 30%. You'll have glass with specific properties, very resistant. It's usually chemical Pyrex glass has this composition, around 13% of B2O3, and very little aluminum. There is also lead glass that we sometimes name crystal. It has around 1/4 of lead oxide by weight, and it reflects light much stronger than other glasses resembling precious stones. One more interesting group of silicate polymers is siloxanes. It's infinitive chain of silicon, oxygen atoms like this: silicon, oxygen, silicon, oxygen, silicon, oxygen, so on, with two other substituents being organic groups. It can be methyl group. In simplest case, it can be any other organic residue. These polymers are base of so-called silicone polymer and have multiple uses in industry.